We can continue. So are there any questions so far on general properties of parametric representations, graph polynomials, power counting, divergences, convergences, analytic continuation, integration by parts, these kind of things? Because after all this preparation, we can finally apply these things and compute Feynman integrals. So it took us 2.5 lectures to define Feynman integrals. So let's go. So what I want to do in the remaining 25 minutes maybe is to just give one example of a calculation of a Feynman integral in this Schwinger parameter setup using iterated integrals. The idea here is that, well, on one hand, these direct integration techniques are extremely special. So whenever I give you another Feynman graph, it will have another graph polynomial. You're looking at a different variety. Things can be completely different, and in general they are, which is exactly why computing Feynman integrals is an eternal business, right? I mean, you can solve 1,000,000 Feynman integrals, and there will always be somebody who finds a Feynman integral which does not fit into your setup. So anything I could say from now on will only be applying to a very small set of Feynman integrals. One general thing that you always have is a differential equation. So if you have a Feynman integral that depends on parameters, you can always ask the question, what is the dependence on these parameters? So the things that you always have are like the parametric representation. You always have that. You can always analyze the convergence from the Newton polytope. You can always compute the dimension of the number of mass integrals. You can always think of these things, difference equations in a space. In principle, you can work out relations. Of course, in practice, it may take a long time to do that. And you can also, so just as you can compute the difference equation always, you can always compute the differential equations. The question is, can you solve the differential equations? And then it depends on the structure of the differential equation. So who has seen differential equations for Feynman integrals? Okay, not as many as IBP, but some. Who has computed an integral from the parametric representation with polylogarithms? Oh, almost as many. Awesome. But not quite as many. So let's do that in an example. And the idea here is that the message should be that from taking this parametric representation, you can understand, you can learn a lot about the integral, sometimes even before doing the integral. But we'll talk about that tomorrow. Today, I just want to go through a calculation, just as I did on Monday, and then afterwards we figure out what we actually did. Okay. So we look at an example. And we look at the massless off-shell triangle in 4 dimensions. So we have a graph like this. I'm using the same symbols just because we've used them throughout. Normally, I would probably call them differently. With edges 1, 2, and 3. So what are the graph polynomials? For one loop graph, it's always just the sum of the 3 Schwinger parameters. And the F polynomial, we discussed this last time. You do these 3 ways of cutting it. So if you chop off Q, you have to delete x1 and x2. If you chop off this vertex, you have to delete x1 and x3. And for the other one, which is p prime squared, you have to delete 2 and 3. So these are the polynomials in this case. So no mass terms here. And I want all of these momenta to be non-zero. And I want to be in the Euclidean region where they're positive. And then we can think about analytic continuation afterwards. And then we have the superficial degree of convergence. So in this case, we just have 3 edges, and then just all take them to the power 1. And we have 1 loop. So in 4 dimensions, this is just 1. And then with the setup, the integral looks like the following. So the Feynman integral So there was a gamma factor in front, which is just 1, so we don't have to worry about it. Then we have the integrals of the Schwinger parameters. There's also no gamma functions here. This is just because we have these propagator exponents all set to 1 in this case. And now I'm using the representation with the U and F polynomial, so we have this freedom to choose some delta function. And if you work out the exponents of U and F by the formula I gave on Monday, you see you just get the product of U and F. I mean, one way to check that you get the right result is the following. Well, first of all, it has to be homogeneous. So this is linear, F is quadratic, so the denominator is cubic, and you have also 3 integrations. So overall, the thing is projective. If it weren't projective, the delta function wouldn't make sense. So that's a good sanity check. And the sum of all the exponents in the denominator has to be the half of the dimensions. So if 2 polynomials, 2 is the half of 4 dimensions. So this is the right representation. And let's try to compute this integral. Okay. So the first integration we can do with high school calculus. But I still need my cheat paper. So let's choose just for maybe that's already interesting to discuss. So we can choose an arbitrary h here, right? So one thing that's very often used is you put h to be the sum of all the Schwinger parameters. This is nice because you set the sum to 1, so you're actually integrating over a simplex, which has a nice geometric interpretation. The integration domain is compact, and it's cool for many reasons. And also another thing that happens at one loop is that this delta function kills your u, because this is exactly u. So u is 1, so this is gone. We only have to look at the f polynomial. The downside is, well, what happens to the f polynomial? Well, in the beginning, the f polynomial has a special property that's linear in the individual x's. I mean, it's quadratic overall, but there's no x1 squared. Right? So at the function of x1 only, it's a linear function. Now, if you do the substitution, so say you replace x3 by 1 minus x1 minus x2, then this is gone. Because now you have a term x1, x3, and if you substitute x3, then this is a quadratic in x1. So if you use this delta function, already at the first integration, you have a non-factorizing quadratic thing to integrate. So you have to take some square roots to do the integral. So we're not going to do that. So we just take hx to be x3. So we just set x3 to 1 and integrate over x1 and x2. And now, because both polynomials are linear in x1, say, we can just do a partial fraction decomposition of the integral. So we still have to integrate over, or maybe let me just write. So if you use this delta function, so we look at the integrand uf, then we can do a partial fraction decomposition. Never sure how to write this. So let's look at the f polynomial as a function of x1. So I keep the terms which depend on x1. So it has a minus q squared x2 minus p squared. And then there is a constant term in x1, which is just minus p prime squared x2. Remember that I have set x3 to 1. So this is f rewritten. And I want to do a partial fraction decomposition, so I make sure I put the coefficient of x1 in the numerator. And now I have the u polynomial, which is just x1 plus x2 plus 1. So what happens when you bring these things on a common denominator? Well, in the numerator, the terms proportional to x1 cancel, right? This is exactly why I chose to write it this way. And then we have to divide by the thing that remains in the numerator, which is something like x2 plus 1 times what we have there. prime squared x2. Does this work? No, there's a minus, right? So this is a plus. So this is a partial fraction decomposition. And now it's trivial to integrate over x1. Right? So integrating over x1 turns this here into the logarithm of x1 minus q squared x2 minus p squared minus p prime squared x2 divided by x1 plus x2 plus 1. And we have to evaluate this at 0 at infinity. And this is not dependent on x1. So now the next step, which is already the last integration step, you have to integrate over x2. And now we face a problem that in the beginning we did manage to avoid by choosing the delta function cleverly, but now we have to face it. That we have a quadratic equation in x2. Right? So for the next integration, we have this logarithm evaluated at these boundaries divided by this quadratic function of x2. So let us just give a name to the roots of this equation. So the denominator, so introduce variables z and z bar such that the denominator becomes minus q squared x2 plus z x2 plus z bar. Right, so it's a quadratic equation. I can talk about the roots of this quadratic equation. I call z and z bar minus the two roots of this quadratic equation. And if you work out what this means, this is actually just equivalent to reparametrizing the kinematics such that p squared is q squared times z bar, and p prime squared is q squared times 1 minus z bar. Yeah, so equivalently, I could have told in the beginning, let's parameterize the kinematic dependence in terms of these variables. So trade p for z and p prime for z bar in this kind of way. And that just means that we factorize this quadratic in the denominator. So now what we're left to do is to compute the integral. So this triangle now, we have to integrate x2 over this denominator. So again, we can do a partial fraction decomposition, which is now very simple, of this thing. And then you're left with q squared z minus z bar. And then you have the integral from 0 to infinity. And I will not write x2 anymore, just x for simplicity. What are we integrating? Well, just dx over x plus z times this logarithm. And if you evaluate the logarithm at these limits with these coordinates here, then the expression you get is just x plus 1, x plus z bar divided by x times 1 minus z bar. So this is the first term of the partial fraction decomposition. There's another one when you take dx2 over x2 plus z bar. But because this thing is symmetric in z and z bar, we can just write this as the same thing with z and z bar exchanged. Yeah. Any questions until this stage? So we've just written this triangle integral as an integral over a logarithm with the linear denominator. So there's a lot of linearity in this game. So you see that the arguments of the logarithm are linear functions of x. And also the denominator now after the factorization is a linear function of x. And now if you remember what Johannes has mentioned on Monday, is that it turns out to be extremely beneficial to give a name to these kind of functions, these iterated integrals. So are these contour of polylogs which are exactly defined to be iterated integrals of inverse linear functions. and they have nice properties. They're all linearly independent. You have algorithms to deal with them. But for the purpose of this calculation, let's just try to get to the answer directly, as directly as possible. So one useful lesson of this way of thinking of iterated integrals is to slightly rewrite what logarithms are. So there are polylogarithm functions. So there are functions Lie k of z, which are actually multivalued functions, but you can define them by a power series near 0, where you take z to the k, little n, z to the n, n to the k, which gives you, for example, if you evaluate z at 1, the Riemann zeta values that have already been mentioned. So in particular, we have Lie 1 of z, which is just the sum of z over z to the n over n. And you might recognize this is nothing but a slight rewrite of the logarithm. Right? This is the Taylor expansion of the logarithm. But the advantage of this representation is that you see in this representation it's easy to write down what the integral of this is. Yeah, so you see that this is the same as z d by dz of Lie 2. Right? Take z d by dz of Lie 2, then you multiply with an n, so you decrease the power of n in the denominator. So in other words, if you have a Lie 1, or if you have a logarithm or a Lie 1, and you divide it by something linear, by z in this case, you immediately know how to write down an integral by using Lie 2. So all you have to do is you rewrite this thing such that, well, your given variable is this x plus z here, so this should play the role of z. So somehow you want to rewrite everything in terms of Lie 1, where you have x plus z in the argument, or something proportional to it. And of course, that's not very difficult. I did the homework myself, so I'll give you the answer. So you find, if you take this logarithm that we have, x plus 1, x plus z, z bar, x 1 minus z, 1 minus z bar, right? Then you can rewrite this as follows. It's a Lie 1 of z over x plus z minus a Lie 1 z minus 1 over x plus z. And I have another Lie 1 where I have z times 1 minus z bar over x plus z. And then I have two more terms. One is just the logarithm of x plus z. And then I have a constant term, which is just the thing from the denominator here. Log of 1 minus z, 1 minus z bar. So if you know polylogarithms, or if you study them for a while, you will see these kind of identities abound. So there's a lot of functional equations between polylogs of different arguments. But at grade 1, these are trivial to check, right? I mean, just rewrite everything in terms of the logarithm, and you know exactly the functional equation of the logarithm. It's just the functional equation log of x times y is log of x plus log of y. So you can check this in 1 minute if you just expand this in logarithms. So this is a trivial identity, but it has the advantage that now we have x plus z always explicitly as an argument. Okay? So now we can write down a primitive of this integrand. Okay. So the conclusion is that the triangle integral that we want to compute is the following. Well, we have this prefactor. Then how do we find a primitive? Well, as I said, we just have to upgrade Lie 1 to Lie 2. Now the argument is not precisely z, it's 1 over the thing, so we get a minus sign from the integral. Yeah, if you do the same thing with 1 over z here, it just means you get a minus sign. And the fact that you have some constant with respect to x doesn't matter, because this is a logarithmic derivative. So if you multiply z by something, it cancels in this ratio. So you can literally just replace Li1 by Li2 and change the sign. So we get Li2 here of z1 minus z bar x plus z. We have a Li2 from here. We have a minus Li2 from there. And then we have these two terms. So this is easy to integrate because this is log of x plus z divided by x plus z, so it's just half log squared. So we get a half log squared x plus z. And this is just a constant, right? So if you integrate this thing against 1 over x plus z, you just get this thing times the logarithm. So we have minus log of x plus z times log 1 minus z bar. So this is x plus z, yeah? So this is just the primitive of this. Now we have to do two more things, which I don't know how to squeeze in there. So we have the same thing where we replace z with z bar and subtract this. Yeah, this is here the other term from the partial fraction decomposition of the quadric. And then we have a big closing brace, and then we evaluate x from 0 to infinity. Right? This is what we have to do. We have to evaluate this function at 0 at infinity and anti-symmetrize with respect to this involution. So we're almost there. Now, anybody has a suggestion about the value at the upper boundary? What happens when x goes to infinity? What explodes? Indeed. And what is the polylogarithm at 0? Yes, because the power series starts at 1, right? So the polylogarithms are defined such that they vanish at the origin, which is exactly, I mean, you can write this Li1 in many different ways. I chose exactly a form where at infinity they are evaluated at 0. I mean, there's a little problem maybe with these logarithms, right? So these logarithms might blow up. And individually, actually, these logarithms would blow up. I mean, log squared of x, I mean, that goes to infinity. But don't forget this term, right? If x gets very large, you can forget about the z. It's just log of x squared. And that does not depend on z or z bar. So it actually gets subtracted via this subtraction. So the terms at infinity, they actually cancel. So all you have to do is to plug x equals 0 in this expression and anti-symmetrize. And you're done. Almost. So the conclusion is that our triangle integral is 1 over q squared z minus z bar. So what do we get when we evaluate at 0? Well, the first just becomes Li2 of 1 minus z bar, right? The second becomes Li2 of, Li2 of 1 minus 1 over z, I think. Yes? the other one just becomes Li2 of 1. And Johannes already gave this a name, so this is zeta of 2. And then we have a half log squared z, and we have minus log z, log z log of 1 minus z, 1 minus z bar. And then we have to anti-symmetrize. So this is our expression that we get for the triangle integral in this case. And you could say you're done. But as I said earlier, there's a lot of relations between these dilogarithms, and you can actually write this in a more compact form. And how to derive such relations, how to do these kind of operations, I will explain in much more detail tomorrow. For now, you can look up these identities in textbooks, for example. So there is a very nice book by Lewin. There is a million papers on the dilogarithm. And these identities are extremely well known. So we can use identities such as this one, which is a reflection identity for the dilogarithm, which tells us that this is zeta 2 minus Li2 of z minus Li2, minus log of z log of 1 minus z. So this is a true identity. We also have an identity to rewrite this thing, which is our second term, which is one more term. So this is also just Li2, essentially, up to some logarithms. So there's a minus zeta 2 in this case, and log of z log of 1 minus z minus a half log squared z. There we are. Now you can plug these two identities in here to rewrite these two terms in terms of just Li2 of z and z bar. And then you can swap the sign by using the antisymmetry to replace the z bar by z. And now, after the dust settles, this is again a little calculation you should do if you want to check you understand this kind of computation. You finally get that this integral, the triangle, is, so there's a little factor of 2, which you can pull out afterwards, q squared z minus z2. And then what's left after these substitutions is Li2 of z minus Li2 of z bar plus log of absolute value z. Remember, this is just a half log of z plus log of z bar times log of 1 minus z, 1 minus z bar. And I think that's what many people would consider the final answer for this integral. You realize actually if you assume that z bar is the complex conjugate of z, you realize actually this is a kind of an imaginary part, right? Because you have the expression and then minus the thing where z is replaced with z bar, so minus its conjugate. So it turns out this is actually the Euclidean sheet. So if z is equal to z, if z bar is the complex conjugate of z, then in this case you can actually think of the term in braces as 2i times the imaginary part of Li2 of z plus log of absolute value z log of 1 minus z. And this thing is called the Bloch-Wigner. I mean, the whole thing is called the Bloch-Wigner dilogarithm. Which has many special properties and plays a huge role in number theory. But all I wanted to show here is how you can take this parametric representation and just try to integrate out these variables. And here we had an extremely special situation. So what we used here was that in the beginning, the polynomials were linear. We found a variable such that everything is linear. Then we can do the first integration with logarithms. Everybody can do this. Now at the next stage, we had to introduce new transcendental functions. We used the style algorithm, and then we solved in terms of the style algorithm. So you might be complaining at this stage because I told you that we computed this integral, but all I've done is I've rewritten it in terms of another function which is defined as an integral or as a sum. Right? But the point is that this function, right, it's written down there, you know exactly what its differential equations are. We know that this function and this function are linearly independent, so we know that there's no relations here. We cannot simplify this expression anymore. You can compute the monodromies in this representation very easily. So if you have a representation in such a form, even though it is still an iterated integral, you can basically do everything that you want to do with it. And we have crucially exploited this linearity. And the idea about tomorrow is I just want to give a brief sketch of how this, to which extent this can be generalized and applied to Feynman integrals, and give a couple of examples and maybe explain some tools, some computer programs that you can use for this. So for today, I would finish here unless there are any questions on that calculation.